Welcome to this masterclass. I'm Twan. I am a technical artist. I've been working at Ubisoft for 10 years. And in this masterclass, we're going to do a heavy bit of programming and wrangles in VEX and in Python. We will be focusing on biome generation, and this will deal both with the selection of biome areas and the importation of files and dealing with external files to control your pipeline. Let's get into it.
Okay, let's get started. Let's make a height field. So I'm just going to type tab height field in the object context, and it will generate for me a geometry node with a height field inside it. So to start, we're just going to add a noise. So height field noise. And I'm just going to change the noise type to a simplex. That way we have a very repeatable terrain for everyone with a much smaller scale, or at least perceived scale, and some steep terrain. So let's add some detail. Let's do a feature, light field mask by feature. In this case, I want to mask all the medium slopes. So I'm just going to increase the contrast towards the middle. It should be about right. And now I want to convert all these areas to a terrace. So I'm going to add a terrace. And right now it's doing the entire terrain, except we want to first compute the range to be able to do the entire terrain, but we also want to use the mask. Instead of computing the range, you can also type minus 10,000 plus 10,000. But if you type not a symmetrical, or if you don't use the compute range, then sometimes it will smooth your result, which we don't want in this case. And now we actually want to filter out all these small areas. So to do that, we are going to add a blur. It's a height field mask blur. Or you can do a height field mask expand, because in fact it's actually the same node. It just the default settings are different. So what I'm going to do, actually I'm not going to expand at the beginning, I'm first going to shrink. And I'm going to copy paste this node. And with the same value, I'm going to expand that. And to make sure that the value stays the same, I'm just going to copy the parameter and paste the relative references. So now I can tweak this value to filter out all the small parts of the mask. And then finally we just blur it back to get rid of the hard transitions. You can still see there is some square shapes because of the expand and the shrink. So to counteract that, we could do a distortion. And the other one. Height field distort. And then instead of the height field, we actually want to distort the mask. So now, yeah, it's just moving the mask around a little bit. And then if we blur that, we can hide all the square effects. Or we could do the distort after the blur to get a similar result. But these are all up to you in the end. It's just a very basic setup for the terrain. And please refer to all the amazing work that they have done on Project Pegasus for a very good terrain workflow tutorial. This is just an alternative way to do some parts of that workflow. So let's clear the mask. And finally, let's do a erosion. So a Heightfield erode. Might take a while depending on your machine. And then I'm actually going to freeze the frame. I think a bit less. Let's say 10. So that actually removes the time sensitive flag also. So you can see the badges here, like the time dependent badge is now gone. So if you accidentally move your frame around, it no longer will recoup the entire network, which you probably don't want to do in this case. Okay. So finally, let's do a cache. I think file cache. And in this case, I mean, again, this is going to be totally up to you in the end, but I'm just going to use an explicit path. Just going to do call the sub Heightfield, and that will construct the path into this node. I'm going to remove the frame number, and I'm actually going to remove the hip name as well. So now finally we have a relatively simple file name. And yes, we just need sync frame. Oh, actually, we can disable time dependent here also. And now we can save the disk. Okay, now we have the basics. Let's add some more data. So I guess one thing we can just quickly do is maybe add a little bit of more noise on the flat areas, just for fun. So just and to demonstrate that because we have a procedural pipeline, we can just add new segments to our algorithm wherever we please. So let's add a feature. I think we can put it right after the terrace. Oh, not this one. That is the new occlusion masking SOP, but it's for geometry. At least it does other things as well. Heightfield mask by feature. So this time we're just going to add a mask for the really flat areas. And we're just going to keep the lowest part of the ramp. And in this case, I'm just going to use the minimum and maximum slope angles to control what I want. I'll do a little bit of a mask blur. They're not so strong, maybe only 4. And let's add some more noise. So Heightfield noise. Using the new mask, we get a very strong effect, but in this case we can reduce the amplitude to maybe 2 meters and really reduce the element size, I guess, just to demonstrate, let's move up the amplitude again and reduce the element size to control like what is the scale horizontally that we want to apply the noise. So maybe go on. Let's do 50. And now we turn back the amplitude. In this case, it's important to keep center noise because you want to have the noise relative to the input. And I'm just going to tweak it a little bit. Okay, so now just to compare, if I just select all these nodes and turn them on and off with the pass-through flag, we can see that we add some new detail. Okay, let's rerun the erosion. Okay, and now we are going to add some more actual data. And by that I mean new layers. So we already get a lot of free data from the erosion map, the mesa, but especially the sediment, the water, and the debris. And we will heavily use those in the future. But let's add some more first. Yeah. So let's add another mask from feature. This one. And the mask to feature will set the noise mask. And I think if I add a new one here, not exactly sure. Yes, so then it won't directly add a new mask layer, but what we can do is just render it as a mask and then rename it later. Oh yes, what I wanted to do was add a visualize Heightfield visualize, just to temporarily remove the, so no change. Well, we remove the material and we keep the tinting as it is. So just to not visualize the Heightfield coloration. So now I'm just going to make this a linear ramp, and I'm just going to set it from between 0 and 90. And now we have a mask that actually directly corresponds with the slope of our terrain. Okay. So what we can do is with a name sub, and first let's use a blast sub. Well, I guess I'll do that after, just to demonstrate. So let's group the mask layer and let's rename it to slope. So now we have a slope layer, and here we have a mask layer, and now we just want to merge them back together. The only problem now is that all the layers are now duplicated, so we just have to make sure that we also delete all the other layers in here. So we just want to keep only the mask layer. So now we have 8 volumes here and 9 volumes here because we now have the slope. Perfect. Mask to slope. And now we will do another one. And in this case, I'll just copy paste the mask to feature. And instead of a slope, we will mask the occlusion. And we will do a little bit of tweaking to these values. So maybe we can make it a bit more aggressive. So I want to flip the gradient in this case, because the occlusion is the amount of darkness instead of the amount of lightness, at least in that's my preferred display method. And I think we can tweak a little bit the gradient like this. But if we want it to be more exact, what we also can do is just add a Heightfield triangle. And we'll just do a little bit of a short VEX script. At the maximum occlusion. And we will remap that to 0 and 1. So if I just, right now, it shouldn't do a lot. Or at least it will make the mask all the same color. And this was basically the same as the input. But now we can tweak how the occlusion is biased. And in this case, I think I just bias it such that the occlusion is twice as strong as normal. Then I'll just copy paste these nodes as well. And then instead of a slope, we will name it occlusion. And then I can also add that one. And now we have an occlusion mask. Okay. So now we just save again to disk. And now we can start using this data in our next part. Okay, so now let's actually do something with this data. And this is also where this approach will start to diverge from the workflows that have been used on Project Pegasus. Let's first create a simple null node. This is just good practice. I'm just going to call it out. And then to separate the parts of the network, I'm just going to put everything, what we're going to do next, in a new geometry node. Just call it a new geometry node. And now I can hide the other one. And let's start with an object merge. And let's get the data from the other network. Yeah, perfect. Okay, now I'm going to add one more tray layer. So I'm going to use a blast node to keep only the mask layer. I'm going to name it Biome. So now we have one layer called Biome. Now we can just merge it back to the other one. And now we will start doing some coding. So let's get a Heightfield wrangle. So to convert this terrain with all the layers into a biome map, or for example a splatting ID map, whatever you want to call it, you want to do this either handcrafted by painting them in or by using some rules. And these rules can be simple, such as, for example, biome equals slope larger than 0.5. You won't be able to see anything because it's not a mask layer, so let's add a visualize. Heightfield visualize. And let's remove the material and change the tinting should be. No, custom tinting. And I want to use the Biome. And I'll just use a different preset, such as infrared. And I'll just compute the range. I mean, right now it's only going to be between 0 and 1, but we'll change that. And it's only going to have two values right now, either 0 or 1, because that's what we put in our wrangle. If the slope is larger than 0, it will be 1, otherwise it will be 0. All right. The problem with this, I mean, for example, what you could do is start with Biome 0 and then do an if statement and then say, for example, Biome is 1 and do an else if statement, and then, for example, inclusion is larger than 0.5, then it becomes Biome 2. So if I do that, because actually, yeah, so now the values are 0, 1, or 2, because I want integers. So now I have to recompute the range, or just manually put the range myself. So now we have 3 different biome levels, but this system is not very scalable. So that will be the main task we're going to accomplish with this workshop. So I guess one more thing I'll do to prepare us is to print any value. You have to be very careful, so I'm just going to put it on manual, the update mode. If you use a printf function and you want to see the biome, then with a volume wrangle, it will print it for every single voxel. There is there's no way to do this via a group, because it will be only the entire layer that you can select, or at least that I'm aware of. So with a wrangle looping over geometry, you can just say, for example, if the point number equals 0, then do the printf. To do this in a wrangle, we will use if dx is 0 and dy equals 0, or, well, we'll do 1 just to be sure that it will print something when it's not 0, because if I mistyped the attribute, then it will revert the value to 0. So it will only be 1 if the attribute actually exists, or the intrinsic. So I'm just going to remove that, and now I'm going to put it back on auto update. Okay, so this one typo. Okay, so that didn't work yet. Oh yes, of course. Okay, so was it ix and iy? Yes, perfect. And maybe iz. Well, I guess in this case the chance is pretty large that the biome is going to be 0. But at least we see it only prints one value, which is what we want. I mean, we could print the entire volume, but it will take more than 10 minutes, so let's not do that. Instead, what I'm going to do is make a list of all the available attributes. So let's make a list of all the attributes. So that's going to be yes, okay. We'll have something better for this later, but for now let's just do a convert of the Heightfield. So convert Heightfield, And this will convert all the attributes to point attributes. So we'll replace this with something else later. But now we just use it to get our attribute names. So string attributes equals detail intrinsic of the first input or the second input. I get just 0 first, second, third of the point attributes, because we have them here as point attributes. Okay, so now if I am on points or ix1 and iz0, iz1, I'm going to print the attributes. So let's see if that does it again. Okay, so no, so it must be iy then. Okay, nothing yet. Okay. So right now it's not printing anything, and this can sometimes happen when processing volumes. Because if there is no value change on a wrangle, then sometimes it optimizes and doesn't actually cook anything. So one way to force the evaluation can just be height equals height, for example. And now we should get a print. Yes, there we go. So now we can see all the point attributes. So if I delete all the attributes, then I should only keep the p attribute. There we go. Now we get all the attributes again. And this is also why I put an underscore here in the name, because now if I print all the point attributes, it will always show up at the beginning of the list, which will be useful for us later. Okay, so now we know how we can print the attributes. So let's also print all the values. So let's make a float array attrib vals. Also, I'm going to make an integer variable called nattribs, which is equal to the length, well, in this case, len of the array of the attributes. So I know how many attributes there are. I'm going to resize the attrib vals array with attribs. Attrib vals. There we go. So now I have an empty float array that is the size of all the attributes, which right now includes the biome and the p value. We'll deal with those later. Also, I'm going to make an I variable. So then we're going to loop. And I don't need to define it again here because I already defined it outside of the loop. I find that if you reuse variables, then sometimes you get a tiny bit of extra performance. It's not going to be super relevant in this case, but I just do these by default now. So I'm going to loop over all the attributes, so nattribs. So now I have created a for loop, and now I need to stash all the values inside this array. So we can do that by volume sampling. With the name of the attributes, because they are the same name as the name of the height field. And we're going to sample them at the position. So we have to do it this way, because if you want to use the bound version, so for example, slope, you can't do that in a dynamic way. So if you want to type out every variable, you could and make the code a bit longer, but this way it's going to be more scalable, which is going to be the main goal of this workflow and workshop. So now normally, if I just add a second printf line, that, and also \n just to put everything on the next line again, and print all the attribute values. And then if I just move my thing, then I get all the values. So now, for P it's gonna be 0, well I guess yeah. And it's going to be from very small values, some larger values. And normally it should be in the same order as the other one, I guess. Okay, we don't need the UVs for sure. And so I guess I can get rid of those at least. Oh. And also a quick way to force reevaluation is by holding control and just click on the lock node and on the lock node again. If it's the first time, you'll get a pop-up warning you that you will lose your results. Okay. So do I have values that make sense at the moment? I'm not 100% sure. Like for the height, it makes sense. Okay, the bedrock is also a height value. It's not like a mask value. So I think all the values make sense. So then that will give us the basis to actually start making some rules and applying them using this basic code setup. Okay, let's actually make some procedural rules now. You might notice that I have opened up Excel. You can also use OpenOffice or whatever CSV editor that you want. So we're just going to make a very simple CSV editor file. Can even be a notepad because it's the most simple representation of the data that we want to use. If you prefer to use something like XML or JSON, then you can adjust your pipeline to use that instead. But for now, we'll just use a CSV file. So what I'm going to do is make a CSV file that has data in the same way that I have height fields. So for every relevant height field, I'm going to make a column in my CSV file. But the first column I'm going to make is biome name, because that way I can actually make it easier to debug later and actually see what I'm creating, because just relying on the number is very efficient, but it's a lot more difficult to work with. So let's create a biome name, and now also I can just click on the little eye here and just spin it so it won't go away once I click away. It's just a bit difficult to, well, I guess I'll just put it over here. There we go. So yes, okay, so that won't work. 1 second, let me move that here. Perfect, okay. So the columns I'm interested in for now, if I just walk down the list, because I think the order of height fields is more in the order that you created them than the order that you would have here. So let's try to do this somewhat alphabetically. So let's do debris. Oh, sorry, and without an underscore, because we want to use exactly the same name as the name of the height field, for the reason that if I convert the height field, I also get exactly the same attribute names. So cliffs, debris, occlusion, slope, and water. Okay, and I also want sediments. So let's do that. I think these are the relevant ones for now. But this is I mean, we don't have to do this in an alphabetical way. It's just going to match more easily. Or at least it will be easier to debug this way. But the beauty of a simple system like this is that we can just add a new column later and the system will automatically adapt. So just to test, I'm going to make a few biomes called plains. Well, yes, let's keep a capital. So cliffs, and we shall do something like flooded, and maybe the rock field. Okay, so now what I'm going to do is put some values here that make sense relative to these biomes. So for example, flooded is going to be a lot of water, and most of these, or at least the columns that I took, are specifically values between 0 and 1. They don't have to be between 0 and 1, but it's best if all the values are on the same scale for later. So sediment is going to be also probably present. And I want a low slope. Occlusion can be, no, should be low for this one, because for the rock field we want a higher occlusion. And debris we want not so much. And cliffs you want 0. So this is just a bit arbitrary, but the idea is that we can easily tweak these values later. And we don't have to even go inside of Houdini to tweak them. So this way, if you are working with a larger team and not all your team is proficient with Houdini, or they just want to have an even more high-level overview of the addition process, then you can just have them edit this file and put this file on network drive, and it will drive your entire system, or it can for sure. So for plains, we don't want any cliffs, and the slope should also be low, and we don't want waters. We don't want any sediments, no occlusion, and no debris. So plains is going to be the default. For cliffs, we want obviously to have cliffs, maybe some debris. We don't want really occlusions. We don't want sediment. We do want slope. And we don't want water. And then for rock field, maybe there's going to be some cliffs, maybe some debris. This is the only rule for now that we'll use occlusion. Maybe we'll have some sediment. We can go a bit higher in terms of slope. And we don't want water. So I just picked very arbitrary values. Feel free to experiment with them or slightly different values. So now the important part is to save. And in this case, I already made the file, but in case you're using Excel, I'm going to save as, just to be sure that, okay, so I'm not going to save as a text file, but I'm going to save as a CSV MS-DOS. You can also save as a different CSV format, like this one, but it will cause some minor artifacts later, which we can also fix. But the easiest way is just to save it as an MS-DOS file, and I'm going to save. And so I'm just going to overwrite, and there we go. Okay, so now I'm just going to maximize this again. And now, at first, we're going to just load this file again. So let's do that. Okay, let's actually load the file into Houdini. So to do that, at first we're just gonna add a table import. And this is actually based on CSV as well. So we're just going to do the biomes, and it should be in our hip file, hopefully. Okay, so let's get all our values. So cliffs, yeah, I guess we'll start with biome then, and that's going to be column 0, and it's going to be a string. So let's see if we, yes, okay, we have our file. So now we're just going to add some more columns. 1, 2, 3, 4, 5, 6. So 70 total. And all the attribute lengths are going to be just 1. And you can see that the node is erroring because we're trying to get from data from the same column, and these names don't match the thing that we're trying to search for. But I'm just going to set all the columns 4, 5, and 6. Yes, okay, good. And now we just type all the names. Which is going to be debris, or what did I put? Cliffs, yes. So cliffs, debris, conclusion, sediment, slope, head water. There we go. And now normally this should match here. And this is, I guess, the main reason to put the columns in the same order, because now in the geometry spreadsheet it should match. Yes, perfect. Okay, so now we have our biome import. And don't worry, we'll improve this further later as well. So now, let's just copy our nodes to the right. So instead of using the height field, now we're actually going to use directly our biomes to print out these values. So now if I click this, then we see that we have less attributes because we only get the ones that we're actually interested in for now from the biome, and we'll get all the values still. So that's good. Okay, so now when we have our files imported and we have our basic code framework, just to at least load all the values from the height field, now what we're going to do is compare all these values against our new biomes. So let's do that. And I guess we can also start with like a first little optimization, just to get rid of these things in our output. So in Houdini, the P attribute is always going to be the first attribute coming out of 8-point attributes. And in our case, we also have the biome name. So let's do a little bit of array slicing. So I'm just going to specifically get the name attribute, which is going to be attributes 1, because I know that, well, actually I can do this slightly differently, but I won't. So yes, if I do that and just print the name attribute here, then I should get, after I add a semicolon, the biome name, exactly. And then afterwards we can do a little bit of slicing. So because I don't really need the 0 and 1 index anymore, I can actually slice this array. And this works in the same way as it does in Python. And so now, normally, I should still get that, yes. So now I start the array with glyphs instead of with P and biome name. So now I can put this back. And that. Okay, so like alternatively, what I could have done was slicing before and then put 0 here instead, but now I can just slice them both in one step, so that's probably better. And also because I put the length after the slicing, the rest of the code automatically updates. Okay, so now we need to also, I guess one thing, if you have only a single line of code, you technically don't need brackets. It's all up to personal preference. I'm a new line brackets guy, but if you prefer to have the bracket after your condition, then that is of course fine, as long as it's consistent throughout your code and especially also with your colleagues' work, then that will work. So let's actually get the biome information. So I know that the number of biomes is equal to the amount of points coming from input 1, coming from the table import. I'm just going to make a j variable so we can loop over that also. So now we can loop in two different ways. Either we loop again over all attributes and then inside that loop over all biomes. But I think it's going to be better to loop over all the biomes and then over all attributes. So for I equals 0, because we're just reusing the same variable. I smaller than biomes, like this plus. And then we'll just copy paste that. And loop over n attributes. don't forget to put J++ here, J++. This is just also a personal thing I do. I do the indexer of starting from I going upwards, and then the maximum condition, generally NM, etc., or I give them a proper name. Proper names are generally better. So why does that not work? And biomes is undefined. Okay, I think this way. There we go. A little typo. So now what we're going to do is we're going to get the distance between quotes between the values that are on the height field and the values that are inside the biome information. So that is just going to be the difference. So I just need to subtract them together. So let's do that. And because we named the attributes exactly the same on both sides, we can just do almost direct comparison. Yeah. And we know that all of them are float attributes. At least that is how the system is set up, that all the rules are basically floats. I can just get the point information directly here. Also, because I like to define all my variables outside of loops, because then you know that they won't be re-initialized inside the loops. So biome val equals the same attributes, and the attributes going to be J because it's inside the attributes loop. And then the current biome point, which is I. So it's the biome point and then the attribute, I guess the J from inside. Hopefully you're following. So now we need to get the information from here, and this I can just copy paste and just replace this I with a J. And then I'm just also going to make a biome diff, so biome difference. And I'm just going to subtract both. Where did that go wrong? I'm forgetting something. Yes. There we go. So now this value can be negative, and to fix that, what you could do is to hang an abs outside. But instead, what I'm going to do is doing the square of the value. And this has another advantage, that theoretically, if you are thinking Pythagoras, because you are basically doing a high dimensional distance measurement, because you're measuring the value, like the distance between the value for every different attribute, which is like a dimension. And if you keep adding the squares of every dimension and finally doing a square root of that, then you actually get the real distance. I mean, like it's all very virtual at this point, so it's not really real, but I hope that does make sense. So it solves two issues at the same time. So now I have this difference, but now we want to actually compare this difference with the other biomes, because we're interested in the biome that has the lowest distance or difference between the values on the height field and the values in the biome. So what I'm going to do is going to make a new float array. Biome dists, because we're really doing distances in a high dimensional space. I'm going to resize that by the amount of biomes, and they will all be 0 by default. But I mean, just to be sure, just going to initialize them here again. And then for every attribute, I'm going to add the difference, or the square of the difference. So now I should have an array of all the differences. And let's print it out. And then let's see if that makes any sense. So we don't have cliffs, or we have some debris, not a lot of occlusion, not a lot of sediments, some slope, and some water. So, oh yeah, okay, I guess I'll do another print here. And we should get all the biome names, so let's do that. So let's also make a string biome names, and we'll resize it in the same way. Oh no, resize. And then we actually have the name of the attribute here already. So we just need to do that. And then on point I. And now I can just replace this. And now normally I should just get the biome names also. Okay, so there's not a lot of cliffs, but we do have some slope. So there is some distance to the plain biome, a little bit less to the cliffs biome. A little bit less again to the flooded biome, and even less to the rock field. So that means that for the current voxel, which is IX1 and IY1, normally I want the system to return rock field as the correct biome, because it's the lowest distance. So to do that, we can use a argument sort. So biome dist sort is arg sort, and it's going to be sorting the values from the biome dist array. So this this function returns the order of the array from lowest to highest value. So let's again print that just to show. So yes, so now it's 0, 1, 2. Okay, so it's actually the exact opposite. And you can see that this is the lowest value. This is the second lowest value, the third lowest value, and the highest value. So that actually makes sense. So if I get index 3 from this array, it returns 0. Oh yes, yeah, it's transposing completely. So sorry, the lowest value is the third in the array of the array before. So it's yeah, it still does the same thing, but I explained it the wrong way first. So the lowest value is the third index of the previous array, and then the second lowest is the index 2, etc. So if I want the biome, that is the lowest distance, I just need to get the first value from this array. So what I want to do, in this case I can actually bind equals biome sort 0, because the index of the biome is just going to be equal to the point number here. And now, if I copy paste this biome, we should get some information. Yes, we do. Okay, and I can recompute the range. Actually, in this case, what I'm just going to do is going all the way to 255, or maybe let's do 16, something like that. And we're going to make the ramp periodic. Or maybe do 8 for more color difference. Or feel free to take a different ramp preset or create your own. But now we can see that we have different biomes and they're all procedurally driven. Okay, so then there is one more thing that I want to do on this node, and I just want to add a reload button on this. So that's relatively simple. Just going to edit the parameter interface. I'm just going to add a little button at the very top. Let's call it reload. I'm just going to give it a Python callback script of how.node and then referring to itself. Or you can do how.pwd cook and then true to force the cook. And then normally it shouldn't do anything yet. I mean, I was expecting there to be a little cook. But yeah, let's just change one value. So for example, let's do cliffs and set 0.5. And then save that and then press this reload button. Yes, there we go. So that is a very quick workflow to update like a very large set of rules. So that is the basis of this system. Okay, now we have the rules and we have a way to quickly refresh them. So let's just do this again. We're just going to put the cliffs, for example, back on 0.75 and press the reload button. Oh wait, yes, of course. I do need to save the file first, then press reload, and then you see that again, there's less cliffs than before. Okay, so one thing we're going to add now is a little bit of a fudge factor, if you want to call it that. So what I'm going to do is just to Control X and Control V, just to move everything one column further. I'm going to add a Biomes Weights. And by default, I'm just going to put it on 1. This will serve two functions. One is if we are not completely sure about the values, but we just want to fudge it in such a way that one biome is reduced or increased in the amount of frequency, we can just tweak the value. And the other purpose we can use it for is to put a biome weight exactly on 0, or larger than or smaller than 0, to just completely disable a rule, for example. That can be very helpful for debugging and other things. So let's leave it. Well, I guess for testing we can immediately put the cliff value at 0. So let's save the file. And now if we reload the file, stuff will go wrong. Yep. And that is because the column numbers have now changed. And in this instance, we will just fix it by just increasing the columns just by 1 for each of them. And we'll add a new, oh, not there. Above here? No. Here. Yes, exactly. Just to keep the order the same. And it's going to be an attribute length of 1, and it actually is going to be a float. So now the value should be back to normal. Oh wait, column 1, 2, 3, 4, 5, 6. Does that make sense? Oh wait, no, doesn't. Okay, Biome weights is column 1. Yes, it's a bit tricky to read because there's a lot of sliders. Okay, there we go, I think. Although we still have a different result than before. So let's compare again the files. So biome weight is correct. Cliffs is correct. Debris is correct. Occlusion is correct. Okay, all the files are correct. I remember what the problem is. So yes, we fix the columns here, but now we also have to actually fix it here in the rules, because we hard-coded the second column to be the name, but now the third is actually the let's Ctrl Z that. The third, or index 2, is going to be the biome weight. So if I open the console again and just force a recook, then you can see that biome weight is actually included in the rules. And right now there is no biome weight height field, which there shouldn't be. But we should address that at least. So to do that, we only really have to do is do this, hopefully. There we go. Now everything is back to normal. Because now we start again with cliffs. So instead of name attribute, I think we can do is make this also an array. And we just want the second and third indices, or 1 and 2. Now I'll get an error exactly because I know that header attribute index 0 should still be the name. Oh yes, and this needs to be an array. Okay, there we go. And now the biomes are still correctly named. And I'm going to add a biome weight here. And biome weight is going to be header attributes 1. And we don't really need to store it, so we just need it inside this loop. So I'm just going to copy paste this for 1 second. I'm just going to put it on manual so it will not cook immediately, because the only thing I want to print is the column again %d, and I want to, or maybe I'll be more fancy, I'll do s and d. Nope, Ctrl Z. Just remove all the other ones, and I just want to print the biome name and then the biome weights. Okay, so hopefully that works. Okay, header attributes is not correct. Maybe I need to put 3. And now we see indeed that we have 1011, which equals the data that we put in the CSV file. And so now we're going to update a little bit some of our logic. So just to be sure that we make some new logic without destroying the old logic, I'm just going to make a copy of the node. And what we now have is this biome weight. So if the biome weight is 0, we can actually skip the rest of the calculation here. We also don't need this print anymore. So what I can do is, like, if the biome weight is equal then or smaller than 0, we can just continue. So it will skip the rest of the computation. But I also want to set the biome dist to -1. And right now this will actually have the opposite effect of what we will want to do. So now everything is going to be biome of cliffs, because we basically made the distance 0 or even smaller than 0. So what we now need to do is, in this logic, only count the biome dists that are at least 0 and skip all the ones that are smaller than 0. So to do that, we are going to actually loop through all the biomes instead of, I mean, we'll still use the arc sort, but we will again loop through all the biomes to find the first value that is at least 0. So I'm just making a new variable here, which is biome index, which starts at 0. And actually, I'll just do this, in fact, because I want to keep the value that comes out of this initialization. And then the only thing we need to do, I mean, it's going to be a complex line, is to check if each value is larger than 0. So I'm going to copy the biome dists, and I'm going to loop through them in the order of the argument sort. So this will remap the array counting from small to large. And if the value is larger or equal than 0, we break out of the loop. And now I can just say instead of 0, it's going to be the first biome index that is... Well, actually, let's do this correctly. That the biome index is the first value from the array that is equal or larger than 0. And now I just can put directly biome index. And hopefully, after I add the semicolon, we have something, but not yet. So let's look at our debug again. Let's recompute it. And the eclipse is still 0 here. Oh, yes. This needs to be... I forgot an equal sign there. And now it is indeed -1 here. But it's not yet skipping. Oh, I see what I did wrong. Okay, I've put I here. This needs to be biome index. Because I is always going to be the same value. Because we're not actually changing it in the loop. And I think this will do the trick. After I put it back on manual. There we go. So if we skip this logic, then it's all going to be cliffs because I set it to -1. But otherwise it will completely skip the cliffs rule. And now if I put it back on 1, and I reload the file. After I save the CSV file and I reload the file, now we have our cliffs back. So now let's code the other functionality of the biome weight. So now instead of 0 or 1, we're just going to put 2. And this one is quite straightforward. Okay. What we do now is just divide the final dist by the weight. Because the larger the weight, the smaller we want the distance to be. So if we have a high weight, a distance divided by a larger weight, the distance becomes smaller. So this should do nothing right now because I didn't read out the file yet. So now hopefully, after saving the file again, and reloading, we have some more cliffs. There we go. So now it's artificially increasing the weight of the biome for the cliffs. So for example, if we put it 1.5, we should have a result somewhere in the middle. There we go. But for the best control, you probably want to actually tweak the real values right there. And only use this biome weight for testing or doing little fixes. There we go. Okay, so now we have this part of the system mostly completed. We can probably add some little bit of comments just to be complete. So at the beginning, what we did was load all the attributes, get all the attributes from the points of the host input 1, and we split the attributes into the special attributes that are the biome name and the biome weight and the other attributes. And I think because we now assign the biome here, we can also get rid of this line here. Yes. So what we do here is get all the values from the Heightfield layers. And then what we're going to do here is loop over all biomes. And loop over all attributes. And then finally, so comment out this. Get the biome with the lowest difference or distance between the height field and the biome data. That is at least 0. So what we're doing here is looping over all the attributes, adding the distance for each attribute of the biome. And I mean, we could add some more. Skip biome if weight is 0 or smaller. The weight. Okay, so that is the system mostly working now. And the next part is improving the table import a little bit. So now we have the basic system working, but we did notice that when we added the biome weight, that we had to reshuffle the entire table import. It's a very powerful node with a multiparm, but in this case, I think to make the system even more scalable and automatic, I would like to make a custom version of the table import specific to this case. So let's start with that. For that, I'm just going to create a basic Python sub. And in this Python sub, we're just going to add 2 parameters. So the first one is going to be the same reload as we added to the table import. And the second parameter is going to be a file. There we go. Now for the file path, we can just copy paste the same thing. And we're going to import the CSV library. So to get the file path, let's do that. Equals how.parm file path, which is what we named this parameter. And we go to eval it as a string. And then normally if I print the file path, I should get the file path, or the entire file. So that's good. So let's open the file. And you can actually use some of the automatic tooltips to help you code. And in this case, most of the default values are good, except the encoding is something we'll talk about. Normally, we shouldn't need any encoding, so it should be relatively simple. So we just open the file path as a CSV. Print CSV file. Okay, good. Now we're going to create a reader, which is csv.dict reader CSV file. The limiter equals date reader. Okay, good. Now we can make our headers. Also, be careful. Note that in Houdini, if you use tab in Python, it will just automatically replace stuff with spaces, which is very good. But if you're using an external editor, make sure that you always use spaces or always use tabs. I think the style guide suggests 4 spaces, which Houdini does. So keep that in mind. Reader.fields names, I believe. And let's do that then. Oh, it's just an object, it's not a function. So now, hopefully, yes, we have our headers from our file. So these are all the same. Here we have one thing with the encoding. So if your header starts with some weird characters like UF something, then you have some bit information from the UTF-8 in your CSV file. To work around this, you can actually add some encoding. So to do that would be to simply add this encoding. So it's UTF-8-sig, and it should also fix the issue with the header. The advantage is that with both encodings, this one works. So you can always keep it in if you like. Okay, so now we have all our headers. And now we want to, for each header, actually create an attribute. And then for each column, and then for each row, we want to create a new point that contains this information in exactly the same way as the table import does. So let's do some live coding. So right now, this Python sub does not generate any geometry. So let's keep the default information over there. So for a header in headers, I want to make a point so that it's going to be geo.create points. So now we have 8 points. Okay, yes, we don't want to create a point for every header. We want to create a point for every row. right now we're creating a pointer every column. So let's not do that. So let's comment that for now. So what we want to do is actually add a new attribute for every header. Okay, so let's create a attribute for every header in the headers. So it's going to be geo dot. Well, let's go to documentation also just to be sure. I mean, it's going to be a lot of functions, so I think we're just gonna, yes. So it's just the add attrib, and in this case, we want to just, well, I mean, we can just copy paste it, I suppose, directly here. So the type is going to be how dot geometry type dot point. The name is going to be the header. Default value is just going to be 0 for now, or 0.0 because we want floats. And then the transform we want false, and the create local variable we also want to do false, because otherwise it will create a var map, which we don't need. Okay. Attribute type, not point geometry type. There we go. So now we have a var map. And if we type false here, then we shouldn't, exactly. And we don't need to have the var map. So that's good. Now we just need to create the actual points. So now we see that we have all the attributes, but the biome name is a float. So to change that, we have to put its default value as a string instead of a float. So we're going to make a new variable called default value, and that default value is going to be just 0.0. But if the header equals biome name, then the default val is going to be a string. So now if I use this, now we can see that biome name is a string. Okay, next step. We want to store all these attributes in a dictionary. So let's make an empty dictionary. And then we can just say attributes with the key of header is going to contain the new attribute. So now if I print all the attributes, then I should get all the function calls or all the data, but it's going to be like the full data of the attribute. So no need to do that. So now we have all the attributes stored. So now let's actually process the file. So for row in reader, I mean, just to be complete, let's print the row. So now we see the full dictionary of every row, because it's a dict reader, so it will be easy to actually get all the information using the headers that we already have. So now we can actually use this create point. So point equals geo create point, And now we should have 4 points. That is equal to the amount of rows. And now we want to set all the data. So let's go back to the documentation. So I want to go to points. And create points specifically. That will return a .HowPoint. And I want to set attribute value. Point dot set attribute value. And because I have all the dictionary or all the attributes here, I can loop through all the headers. So now for header in headers, I'm going to get the attribute back from this dictionary. And then I want to get the value. So that is going to be the row and then header as well. So that could be, oh yes, oops. So there we go. So now we have some data. It's not going to be perfect just yet. Because now all the values are going to be set back to strings. And that is because by default everything is going to be a string in the dictionary. So instead we're just going to do a little intermediate step of storing it to a value. And then if the header is not equal to biome name, then we're going to convert val to the float of val. And then instead of row header, we can put val here. Then to comment out the code here. Okay, I made a little typo here. There we go. Because now the default value is going to be a float unless the header is biome name. Then it's going to be a string. And that for the opposite side should be able to just comment out and everything is working as expected. So now just to compare the files again. All the values are now matching. And the big advantage is that now simply plugging the other data does exactly the same thing. So just to make sure we have our old network still available, we'll just copy paste the nodes, import the biome data, and let's add some comments. In Python, that's with hash. Get the file path, open the file, make a reader from the file and get the headers for every header has a new attribute. And then finally, for every row in the file, set the correct values to a new point. So there we go. And now to demonstrate the scalability, let's get some new data actually. So always putting it back on manual when you're moving around the network. I think it's a good habit just to avoid cooking in some cases when you don't want to. In this case I want to, I need to recook it because I want to update this file cache. So let's add some new data here. Let's do a Heightfield flow field. And that will actually output a mask also. So just like before, I can just make this flow. And merge it back into here. Also just to compare some stuff. Let's remove the material and do some custom tinting. So flow is this, and I think it's going to be close to the debris. No, not really. Or sediment. No, it's I mean it's related to all of them because they are generated by the erode. But now we have a separate mask also for flow. So just to make sure that we output it, we just click again on save to disk. And now here we have a flow. Putting it back on manual just to go back here. Now everything should still be the same. So what we can now simply do is add flow, or even better, if we just move all the columns to the right, and flow, I mean in most cases just going to be the same kind of value. But for the rock field we want maybe a bit more flow. To get a kind of a debris in combination with the flow. So now if we save the file and simply press reload. Ah, okay, oops. I made a typo here. There we go. And now we immediately have the flow without having to manually add it into the list here. And the ordering of all the columns is also automatic as long as we control the first two, because those are the only special ones. So now we have a very scalable, simple setup. Like again, for the artistic quality, you can send this ID map and generate a very nice terrain material with different textures based on this map. Or you can use these blobs of the terrain to drive other parts of your network, such as the positioning of trees, rocks, roads, water, you name it. So it's really just a part of your pipeline, or a potential part of your pipeline. So now we have built most of our Heightfield data. So let's take the next step. I'll just move all our work in progress stuff to the right and actually move our final version to the main chain. So right now we're just having height fields, but at any point in our algorithm we can actually go to polygons. With a simple as a convert height field, and we can also bake the point colors in there. Like right now I don't really need the UVs, and we can see that all the layers are now baked into point attributes again. So one thing that's easier to do in geometry, like SOPs, I mean everything is SOPs, but under the hood a lot of the volume operations are actually in COPs, not the wrangles specifically, but a lot of the blurring functions are. But let's actually tackle some of this in SOPs. So what we, for example, want to do is maybe filter out all the tiny parts of biomes and replace it with something else. For example, this one voxel that is of this biome, maybe we want to replace it with the biome just around. So because we have basically all our points, all our voxels as points now, we can just flatten all our data. This is actually the default script that I have on all my point wrangles. If you want to make your own default, just type your code and save it as permanent reference. Save as permanent defaults, or just type it again. And now we have our points here. So one thing I can also just do is we made the biome name in here, but right now it's not yet available on our point data. But it's very easy to fetch. Because the biome index is actually equal to the point number. So we just need to do one thing. And that is changing this biome float to a biome integer, because it is really the index or the point number here, basically. So it is as simple as just getting the biome name using the biome index. And now we should have all our biomes. So now it actually is much easier to debug when you know easily that biome 3 actually equals the rock field. So it will be much easier to tweak the values later. And get biome name. Okay, let's build a little bit of a filter. And to debug, I'm just going to add a color node to replicate what the Heightfield visualize is doing. So let's do some more wrangling. So basically what I want to do is for every point, check in a radius what the most common biome is, and then change it to that. So I'm going to make an array of points using the near points function of the same input inside a range. Then there is one thing I need here, and that is to get the maximum biome. Alternatively, I can check the amount of points here. That also works. I'm just going to get the maximum biome value as a detail. And it's going to be 3, which is going to be basically 0, 1, 2, 3. So actually it needs to be 1 number higher. Okay, let's make some arrays. So what I'm doing here is I make a empty integer array with the size equal to the amount of biomes that are possible. And then I'm going to count up inside the range what the number of points are of each biome. So let's count actually the amount of points that have been found by the near points function. And let's initialize an I variable. So let's loop over all the points that have been found. And let's get the current biome. And then because the biome is just an index, I can simply do this. So now, because we're working on points, actually can just group a single point. Okay, something went wrong. Oh yes. One more closing bracket. Ah, yes, okay. So now I have 4 points, apparently. Oh no, wait, I only have 1 biome point. I have 4 biomes and 1 point is inside 1 biome because the range was 0. So it was only finding its own point. So with a range of 10, we see that the same biome now has 74 points and some other biomes have 0 and 6. So if I use the color node in front, I can select this specific color and I can see that it's vastly more common to have biome 0 because it's going to be biome 0, biome 1, biome 2, biome 3. And what I can do now is again use the arc sort to simply replace the biome. But in this case I want the highest number and not the lowest number, so I can do -1 between brackets. So now, oh yes, okay. If I put the color behind, we can now see a very aggressively filtered biome map. And we can control how aggressive it is by simply changing this range. One thing is that in certain cases it is possible for this algorithm to create some new artifacts or anomalies, let's say. And maybe you want to do some more steps of the filtering. So actually let's put this in a loop. And we're going to loop with a feedback. I'm going to set it on feedback each iteration. And because the biome is always going to be the same every loop, we kind of want to do that before the loop. So in theory you could add another input to your loop and connect it like this. However, when you are doing loops, in particular for each loops, maybe it's less relevant for feedback loops, but especially for each loops, it is much more performant to have linear chains, because they are very good at being compiled with a compile block. So let's do that. So I'm just going to slightly tweak the code first. Let's keep it out of the loop first. So right now it's not doing anything. So we're just going to keep this in the first input, but we are going to rename the attributes and don't delete the original. I'm just going to copy paste this here and then change this to 0. And now we should have the same result as before. Okay, so now I can just put it in a feedback loop. and we see that it iteratively does filtering. One thing is that it's now maybe a little bit too aggressive, and we can see that it also changes with each iteration. So maybe what we want to do is actually scale down the range for each iteration. So one way to do that is actually use a second block begin, but instead we put it on metadata. And this metadata has some detail attributes that we can use. And in this case, we're interested in the I value. It is basically the same as the iteration value, except that because our start value is 1, I value will also be 1 on iteration 0, and then on iteration 2 it will be basically a higher number every time. And this is important because we're going to divide by it. So I'm just going to make another intermediate variable. And then simply divide by the I value. And it's important that we start with 1 instead of 0, because otherwise we divide by 0. And we would get an unpredictable result. So now, if I increase the iterations, basically each iteration thereafter will be less and less aggressive. So you have a natural convergence. So maybe now we can actually put it more aggressively to begin with. And then we get a nice blobby result. Because these shapes are going to be much easier to work with in other algorithms. And also, to get the biome name, we can do this afterwards. To again get all the biome names with the updated biome filtered. Filter biomes. And let's add some comments. Let's get range, scaling down each iteration. Get nearby points. And then what we are doing is for each biome index, find the amount of points that have that value. Set the biome to the most common biome found in the range. That's what we're doing. Okay, so what we can do now is actually continue the rest of the algorithm that is outside the scope of this workshop in polygons, or we can actually continue with it in the form of a height field. So for example, what I can do here is just keep again only the mask and just name. And we're going to, oh wait, I want to keep only the mask. And I'm just going to make a new layer. And again, merge it with the original. And do another Heightfield wrangle. So now we still have our normal biome, but now I'm going to add a biome filtered, and right now it's equal to the mask. But what I'm going to do here is actually get from the nearest point, because we converted all our voxels to points and then flattened it. It's important because a height field will always be at height 0, but if you convert it to points, then the height gets taken into account. And that should do the trick. There we go. So now we have the same biomes, but filtered with this filter. So now your pipeline is set up to continue the workflow using Heightfields, or convert everything to polygons and keep working in polygons. Both have their benefits and downsides. Polygons are much more flexible in terms of having an enormous amount of variables and attributes, I mean. And Heightfields are more performant to render. And you can do things like erosion with it much easier.